structures. All right, then continuing on with where we left off, the last time we talked about single, double, and triple bonds. And when we talk about single bonds, how many electrons are shared in a single bond? 2. What about a double bond? 4, right? 4 electrons are shared in a double bond, and how many in triple bonds? 6. Okay. These are important things to remember as we start drawing Lewis structures, which is our next. Okay, in your textbook, there is a list of steps for writing a Lewis. You have to write a skeletal structure. Once you have that done, what's next? Total number of valence electrons, right? Okay, once you have the total number of valence electrons, then what do? Distribute the electrons, then what? Okay, and then I always like to add one. So when we're doing the Lewis structures, it's kind of one of those things that you learn this. So we have several problems here that we're drawing Lewis structures for. So let's start off with our first one. What we do is draw a skeletal structure. What are some general guidelines to follow when we're drawing Lewis structure? What are some general guidelines? The less metallic is terminal. How do we determine what's less metallic? Its location. Where are the less metallic elements located? We talked about this last chapter. Right, correct. So everything on the right is going to be more terminal than those. What else? What's another guideline? What can I say about this one? If I'm going to draw the skeletal structure, my central atom is typically going, in this case I don't have a metal. Carbon. Carbon a lot of times is when you have carbon, it's going to be one of the central ones. So if you see carbon appear, for this one, when I draw my skeletal structure, I would have carbon in the middle, and I would draw my H's. That would be kind of my little skeletal structure. What's my next step? Figure out how many valence electrons I have, right? So how many does carbon have? 1, but how many hydrogens do I have there?
4.
4. So I'm going to have 4 plus. So I have 8 valence electrons. The way I start to distribute this is I just connect everything to the. Now I'm going to go through and I'm going to put electrons up here, achieve my octets and my duets. Does carbon have access to 8 electrons? How about hydrogen? How many does hydrogen have access? Okay, so we have our octet here, we have our duets for each hydrogen, everything. We draw for the shared electrons, you want to draw lines. So if I start drawing lines all over the place, I apologize. Technically speaking, you're supposed to draw dots for unshared lines. Okay, any other questions on this one? All right, let's look at the next one. N2O. What is our skeletal structure going to look like? NON. Why is it going to be NON?
Oxygen.
What made you guess that? It would be symmetrical that way, right? Yeah, it looks prettier. So symmetry is also important. So that's another guideline. If you can draw something that's symmetrical, so there's our third guideline. So we have an N. Okay, so now we figure out the valence electrons. How many valence electrons does nitrogen have? 5 valence electrons, but we have 2 of them. So 2 times 5 plus oxygen has how many? So now I go through. Obviously, how many electrons have I used at this? 4, so I'm going to have to. So what the next thing you're going to do is, when you do that, how many electrons have you now put on there? How many total are there? I have 20, right? Because what I do is I take, now that I've done that, this would be the Lewis structure for N2O. What is N2O called? Yeah, but there's nothing to take from off. This one right here, this is all it can do. But yeah, if you had to, you take 1 set from each, remove a set from each, and add 1 bond in between. Remember, we just are adding electrons in, and it's like a balancing game. It's not like we're tweaking with the actual compound. We're just drawing a picture. So this is the method that we use to get to that picture. Other questions on this one? Okay, SO2. Looking at SO2, what would the skeletal structure for that one look like? I heard someone say it. OSO. Okay, so there's our skeletal structure. How many valence electrons does sulfur have? 6. And oxygen has how many? 6, but there's 2 of them. So we have a total of 18 electrons, right?
Mm-hmm.
Okay, so for this one, what is SO2 called? Sulfur dioxide. So remember the naming, guys. Don't start shutting that down. All right, so for this one, we connect it here and we fill in our octets. And we get that. How many electrons do I have total there?
20.
I have 20, right? So what do I need to do? How do I get rid of the extra pair? What do I do? Make a double bond. Take a set from each of those, draw in a double bond, right? Now how many do I have? I should have 18. So now what we want to do, double check everything. Does this oxygen right here have access to 8 electrons? Yep. What about sulfur right here? this, that is perfectly fine too. What are these two things called right here? Resonance structures. When you have more than one way of drawing something, that is what we call resonance. It's an added degree of stability to a compound. So what actually happens is this doesn't exist like either of these forms. What you actually have is more something more like this, where they're actually, both of these oxygens are sharing those electrons equally. It's like 1.5 bonds. So it's something more like this, but we can't really draw that very nicely, so we draw these resonance structures instead. So it's just a way of showing that there's resonance. So if you were to draw this instead of that, you get it right. There's nothing wrong with that. These are just called resonance structures. Sometimes I might have you draw all of the resonance structures, so you might have to draw both of them. But just be aware of what resonance structures are and that they do exist. Don't panic if I draw it one way on the board and you're like, but I drew it this way. That's fine. That's a resonance structure. They do exist that way. Okay, questions on this one? Okay. Let's look at the next one. Okay, so for this one, I won't ask you to name that because you don't know it. What is the center atom going to be on this one?
Carbon.
Carbon, right? So we have carbon, and then what's going to surround it? So it doesn't really matter too much where you draw these. So you could draw them basically anywhere you want surrounding it. All right, so for this one, carbon has how many valence electrons? 4. Bromine has how many? 7. There's 2 of those, and then how many does chlorine have? 7 again, and there's 2 of those. What about 30, 40? Oh my goodness, my brain just shut down. 32. So there's 32 total electrons there. So we start off, once again, we draw our lines connecting them, and then we distribute, fill up the rest of our octets. When I do that, how many electrons have I now used? 32. So that is my Lewis structure for that particular compound there. Okay, questions on that one?
When we're doing things like that one, would it matter if you put like, if you didn't have them matching like the 2 bromine?
If you put like a bromine here and a bromine here and chlorine here,
yeah.
No, that's fine. Okay, this one. This is methanol. What do you think the skeletal structure for this one's going to look like?
Is it like H, and then O, right beyond O, and then C, and then 3 H's coming off of C?
Like this?
Yeah.
Yeah. Some of you might have also drawn it rotated. Like that. So they're the same thing, they're just rotated. This is how I would actually draw it, but it's the same thing. So yeah, it's that exactly. So carbon is our central atom. Oxygen is attached to carbon. It is more metallic than hydrogen, so it's going to take one of those places. And then hydrogen will come over here. This is an alcohol group. That's something when we get to organic chemistry you'll learn about. Okay, so we have that. Let's look at the valence electrons. Carbon has how many valence electrons? 4. Hydrogen has how many? 1, but we have 4 of them, right? So there's 4 times 1, and then we said oxygen has how many? 6. So we have a total of 14 electrons there. Okay, so we fill this up, and now we need to complete our octets and duets. Hydrogen, how many does each hydrogen have access to right now?
2.
2. Those are content. How many does carbon have? 8. So we don't need to add any electrons to it. The only place we need to fill up that octet is the oxygen right there. When I do that, how many electrons have I now used? 14. That is our Lewis structure. Questions on that one? Okay. similar to the last one. What's going to be our central atom? The C. So you can pretty much guess where the H is going to be attached. Are they going to be attached to the C or something else here? In this case, they're going to go to that C. So you're going to have an H and an H. Then what else? Something like this. So this one's a little tricky. Okay, so we have that. Now let's figure out the valence electrons. We have hydrogen, we've said, has how many valence electrons? 1, so we have 2 of them plus times 1. Carbon has how many? 4, and oxygen has how many? And there's 3 of those, so we have 18, 24. Okay, so we fill in our lines here. Now, when you do this, you'll notice that we have hydrogens have their duet. How many does carbon have right now? 6, so we need to put 2 more there. How about oxygen right here? It has 4, so we'll draw in those 2. How about this one right here? 4, so we need to draw in 4 more. And how about this one here? It has 2, so we need 6 more, right? So when I draw those in, how many electrons do I now have?
26?
I have 26, right? So for this one, your double bond always going to go kind of in the middlemost and that central atom first. So we're going to put our double bond right here. And then if you look at that, how many, does every atom still have access to 8 electrons? Yes. It should. And then how many electrons have we used now? 24. There should be 24. So we had 26 before. So that one's probably like the hardest kind to get.
Two oxygen together.
Questions on that one? Okay, so far we have only written Lewis structures for neutral compounds. You can also write Lewis structures for polyatomic ions. And yes, you need to be able to do that. So for polyatomic ions, it's fairly straightforward. It's the same concept, except you just have to be aware of the charge. So for example, if we have NO3 minus, I start off drawing my skeletal structure same way as I did before. What is my skeletal structure going to look like for this one? N in the middle, O's around it, right. So we're going to have N, and then we're going to have our 3 O's around it. When I figure out my valence electrons, I did the exact same method. Nitrogen, how many valence electrons did it have? 5. How about oxygen? 6. We have 3 of those. But this time, I'm not done just with the atoms. I have to look at the charge as well. So I have a -1 charge here. What does that mean I'm going to do to my valence electrons? Am I adding 1 in, or am I taking 1 away? Adding 1 in, right? So I have +1. So I do that, and I end up with 24 valence electrons. So now I just fill this in. Make sure everything has an octet here. Okay, so when I do that, how many electrons have I now used? 26. So I have to, and this is arbitrary, just pick whichever one you want. I'm going to erase one of the bonds and make a double bond here. You can double bond any of those, so that's up to you. Which is called, what kind of structures do we have here? Resonance, right? Okay, so now how many electrons do I have?
24.
24. Now, am I done?
No.
Oh,
You have to
bracket
put it
in
in
the
brackets.
This is the step everyone forgets, and I guarantee you people are going to forget it on the test. Don't forget to put brackets on it with the charge on the outside. Those are very important. I give you a chart on the exam, and I have you draw Lewis structures and write the charges and stuff, and if you don't write the charge, you get the whole thing wrong, because it's just a point, so you just lose that whole point. There is no partial credit for that. Yes?
Does it have to be written like that? It's going to be like split backwards, the O on the bottom?
You can, as long as it's the same, like if you rotate it, that's fine. If you have the double bond over here or up here, that's fine. They're resonance structures, so there's more than one right drawing. It just has to be 1 double bond, 2 single bonds.
Okay.
Yeah. Other questions on this one? Okay, the next one we have... What do I have a feeling that was supposed to be HSO4 minus? Whoops. Was anybody able to draw Lewis for HSO minus?
I drew H and then a single bond and F into the top, then double bond, and then an O.
Okay, this is supposed to be HSO4 minus. I left a subscript off there, sorry. HSO4 minus, what was that called?
Isn't it HSO4
Sulfuric
SO4 is 2 minus by itself, so you add an H, it's going to take it away. When it's HSO4 minus, what was that called?
sulfuric acid.
There's a charge there, so it's not sulfuric acid, that's H2SO4.
Oh, yeah.
Hydrogen sulfate or bisulfate, yeah. So that's,
Oh, yeah, for polysulfate.
sorry, it's got I left the SO4 off of there. So when you draw this one, what's going to go in the middle? Sulfur. Now, sulfur exists like this, sulfate is like this normally. So what do you think is going to go around that S? The oxygens. Okay, so this one, a little weird. Okay, so we have our oxygens there. Arbitrary, pick an oxygen, add an H. Doesn't matter which one. So the H is going to go on the outside. So here's kind of our skeletal structure there. Let's figure out our number of valence electrons. Hydrogen, we said, has 1. How many does sulfur have? 6. And oxygen has how many? 6. And there's 4 of them. And then that 1 negative charge means we do what?
+1.
Add another 1 in there, right? So we have 32 total valence electrons. Okay, so here, hydrogen has a duet. It's content, so I'm going to fill up the rest of them. Do I need to add anything to sulfur? Okay, so when I do that, how many electrons have I now used?
32.
Should be 32. And what am I missing?
Bracket.
Bracket and my charge. So, there we go. Okay, questions on that one?
So because you're adding or removing electrons, the charge will always be your positive.
When we're dealing with polyatomic ions, yeah.
But it won't be like 2 minutes. Because you always...
That's the next one. You can have more than
Depends
just
on
one
what the
negative.
charge is of the polyatomic
It
ion.
matches the charge of the polyatomic ion, yeah. Okay, our next one, PO43 minus. What's going to go in the center here?
P.
P. What's going to surround it?
4 O's.
4 O's. All right, so for this one, phosphate has how many valence electrons?
5.
5. Oxygen has how many?
4.
There's 6, right, times
Yeah.
4 of them. And then we do what with the 3 minus?
3.
What does that mean? Plus 3, right? So we have to add 3 on. So here we have 32 again, right? All right, so we fill this up, draw our lines there. So now phosphorus has an octet. We need to fill in the rest of them, so we make the rest of these happy. And when I do that, how many electrons have I used? 32. So that matches this. Now for this one, when I put my charge, don't forget that this is a 3 minus charge, so I'd have that 3 minus on the outside. Questions on that one? Okay, so everyone okay on Lewis structures?
So the brackets only go for ionic, the first ones you did the ionic ones on the anion, and then only for polyatomic ions.
Yes. Yeah, things with charges, basically. Okay, now we're going to go on to the next step here, which is going to be basically the VSEPR, the shapes of molecules. So when we talk about this, we're going to actually start talking about some molecules that have some exceptions to octet rules. There are very few atoms out there that do have exceptions to the octet rule, but we do need to be aware of these. So what are some of the exceptions to the octet rule?
Boron.
Boron, how many does boron take? We know it's an exception. It's probably important to know how many it takes, right? Yeah, it takes 6. So boron will take 6 electrons. What are some other exceptions?
Says nitrogen.
Nitrogen, sometimes an exception. Yep, nitrogen can be a funky one. What else? Hydrogen, helium, lithium, beryllium. How many do those sometimes take? Lithium will take 2. How about hydrogen and helium?
2.
2. What about beryllium? Sometimes that'll take 4. So beryllium can be a little weird too. Magnesium's not really an exception.
It's MgCl2 don't seem to only do 4.
No, magnesium gets rid of its 2, and it gives them this chlorine, so it has that full outer shell. Yes?
I think I read in the book that it actually gives like a few compounds like that. Like there was an SF6, it said could be,
Oh, yeah.
and then there also like
They could have more than 8.
could be,
Right, some of them can have more than the 8. So which ones tend to have more than 8? What class of element over there? There's one class that almost always has more than 8 when it's in a covalent compound. And you wouldn't think of them as being in compounds. There's my hint. Not the halogens. The noble gases. The noble gases, yeah. So like you'll have xenon hexafluoride is what you're talking about, XeF6. That's one of them. You'll also have some of them that like phosphorus and sulfur. And nitrogen, someone mentioned, they'll sometimes have 10. So you can have exceptions in there. So phosphorus is a common one for 10. Sulfur a lot of times will have 12 total electrons around it. So and the noble gases, like I said, they'll a lot of times have the 6 bonds or 12 total electrons. So you need to be aware of those exceptions. As we start talking about VSEPR, you're going to see that we're using these. So VSEPR is the valence shell electron pair repulsion theory. We're not tested on that, don't worry. But it basically tells us the shapes of molecules. So as we're going over those, we're going to see that there are some shapes that have 5 and 6 atoms surrounding them. So you need to be aware of these exceptions.
are you going to use a lot of these other exceptions, the lab ones that you're doing?
We're going to practice those, yeah. That's actually what lab this week is on too. So, and you can guarantee that those will be on the exam. Sorry, what? Okay, so we talked about resonance already. CO3 2-. I'll just draw the one structure up here for you. So we have carbon. Let me just make sure that I have to do the math in my head real quick. So we have 4.
Yeah, I think you're right.
Okay, so for this one, you have one structure like this, and once again, your double bonds can move around. So that's for the carbonate ion. All right, so going on to VSEPR then. So in case you wanted to know, there it is. Now we're moving on. Why do we care about the shape of a molecule? Why does that matter to us? I know you're like, who cares? It's a shape. Why is that important? You guys practice this like later on. You answer questions about if things were polar or non-polar and all kinds of stuff. So why does the shape care? That's a huge part of it, right? So you looked at polarity in your outlines. This really helps us learn how the molecule is going to act. It's going to teach us about properties of the molecule. So we can look at something in 2 dimensions and say, oh, yay, look at that, pretty. But it doesn't tell us very much. We need to know about the shape. The shape is going to tell us how those electrons are interacting with each other, how close the electrons are they repelling, are they attracting, what is going on, which then determines a lot of the properties for these atoms. So we need to know their shapes. Now, I talk about the difference between electron geometry and molecular geometry. What is the difference between those?
The electron is based on the electron, and the molecular is based on the whole atom.
Right, it's just what it sounds like. Electron geometry talks about the shape of the electron, whereas the molecular is the shape of the whole molecule. Okay, and I give you some very specific guidelines in the outline. The textbook, if I recall, it gives a lot of really wordy instructions on this one, so I think I kind of made it a little bit more succinct. So when we're looking at VSEPR, the very first thing you need to do is, you're going to love this one. What do you think I'm going to say?
Memorize the whole thing.
Memorize the whole thing. You got it. Memorize the handout. So you're supposed to go to this website, and this is another place where flashcards will come in very handy. Is that green or red? This one is red. chart, well, I guess the good news is that you technically don't have to memorize the entire thing of it. This chart, you will need to memorize, let's see, what did I put you on here? Molecular shape. So over here, this molecular shape, the electron geometry, the hybridization, and then the bond angles right here, and then also the pictures. So that's what you need to memorize from here, which I guess basically is everything. So there you go. Never mind. Okay. I was like, why did I tell you that? I should just have memorized the whole thing.
Not the lone pairs.
Well, you kind of have to know that in order to do it. So in order to figure them out, you kind of have to know that.
Just do it.
So flashcards are your friends again for this. Now, with Vesper, when you are doing the problems with Vesper, which, like I said, this is our lab today, the very first thing you need to do is write out the Lewis structure for a molecule. Whatever molecule you're trying to find, write out the Lewis structure first. So you're practicing Lewis structures as well when we're doing Vesper. Then I give you a whole series of steps there. So the best way to do this is to just dive in and start doing this. So let's look at BEF2. So when I look at BEF2, my first step, draw the Lewis structure. So to draw the Lewis structure, what's the first thing I do? I draw my skeletal structure, right? So what's going to go in the middle here?
B.
BE goes in the middle, my F's go on the outside. How many electrons, valence electrons does BE have?
2.
2, and how about F? 7, and there's 2 of them. So we have a total of 16, right? So for this one, I'm going to go in, I connect those, and then I fill these up. Now, beryllium is one of those exceptions that I was talking about. It can take just 4. So I'm going to stop when I put 4 in it, and then I'm going to count to figure out how many electrons I've used. How many electrons have I used here? 16. So this is a case where it takes just the 4 valence electrons. If I added in 2 here, that would have been too many. So I know it's content right now. So this is my Lewis dot structure. Once I have this, now I go over to this chart. Remember, the bonded atoms are atoms that are actually bound to that central atom. So in this one, I have 1, 2 bonded atoms. So my number of bonded atoms is equal to 2. That's how I figure that out. The next thing I look at is my lone pairs. To figure out the number of lone pairs, I'm looking at the lone pairs around the central atom. I don't care about these outside ones. I only want to know around this one. How many lone pairs do I have around beryllium? I have none, right? So my number of lone pairs is 0. What I do with this information is I go and I look at my chart, and I look for something that has 2 bonded atoms and no lone pairs. When I find that, what is my molecular shape? Linear. What is my electron geometry? Linear. They're both linear for this one. So when I draw this, it's going to look just like this one right here. So I'm going to draw it out like this. When you are drawing something for Vesper, you do not have to show all the lone pairs of the surrounding atoms. So you don't have to fill in all those electrons there. You're just showing the shape of the overall molecule. Difference between the Vesper structure versus the Lewis structure. You're showing the shape, not the electrons on the outside molecules. The central atom, you would show them. If there is lone pairs there in that central atom, you show those. Yes?
If we do those,
I wouldn't mark it wrong. No. No. That would be nitpicky. Because you're still showing a right answer. It's just you don't have to show the lone pairs on Vesper. Okay, any questions on how I figured this part out? All right, what would be the bond angle on these? 180. Once again, you get that from the chart. Hybridization is not going to make much sense right now, so don't worry about what it means. Just memorize it. What is the hybridization for this one? SP. So that. Don't worry about what it means at this point. Just memorize what it is. In fact, you know what? I'm going to make an executive decision right now. Don't do hybridization. You don't need to do it, so you can scratch off hybridization. One last thing. Okay, any questions on this one?
How did you get the lone pairs?
There are no lone pairs on beryllium.
If
I'm
there
only
were,
looking at the center atom.
if there were lone pairs, it would be like 2 dots, or is it when it's by itself? The valence electron.
We'll do one with lone pairs and we'll go get that when we get to that there. structure look like when I'm drawing the Lewis structure?
Boron in the middle.
So B with 3 CLs, right? Okay, so for valence electrons, how many valence electrons does boron have?
Three.
How many does chlorine have? 7, and there's 3 of those, so we have a total of 24 electrons there. All right, so for this one, we start off, once again, by filling in the center, connecting the atoms to it. Now, boron, is it one of our exceptions? Yes, it can take 6, so we're just going to leave it at 6. Fill in the rest of your atoms here. How many electrons have I used? 24. So this is the way this structure is drawn. This is the Lewis structure. Now I go with this information, and I'm going to try and translate that over to this chart. So looking at my bonded atoms, how many bonded atoms do I have here? 3. I have 3 chlorine atoms, right? So 3 bonded atoms. How many lone pairs? 0. Remember, you're looking at that center atom. You don't care about the outside one. So we have 0 lone pairs. So looking at our chart, what is something with 3 bonded atoms and 0 lone pairs called? What is its geometry? Trigonal. Trigonal planar, yeah. Okay. They're really not that fancy of words. So we have trigonal planar for molecular shape. What about the electron geometry? It's the same, right? They will start to differ a little bit, but we're starting off easy. So for this one, if I was to draw the structure for this one, it looks kind of like a triangle. It would look something like that.
Did you also kind of visualize it as a 3-dimension and memorize
If you can visualize those in 3 dimensions, go for it. I can't visualize things in 3D. I have a really hard time with 3D. So if that works for you, don't even try to explain it to me because I'll be going, sure. So,
Accurate that way, but
yeah, I can't see things in 3 dimensions. That's one thing they say. For some reason, women have a harder time visualizing things in 3 dimensions than men. And this section always shows that because the guys usually do better on it. Usually. Yeah, if there's girls who can see in 3D, I'm so jealous. I have a hard time with it. Okay, questions on that one? When we start talking about polarity, that's when it affects you not being able to see in 3 dimensions. All right, the next one, CCl4. What is CCl4 called?
carbon tetrachloride.
Carbon tetrachloride. So for this one, what will our centermost atom be? Carbon, and what's it surrounded by? 4 chlorines, right? So we got that. Okay, carbon has how many valence electrons here? 4. How many does chlorine have? 7, and we have 4 of those, so we have a total of 32. So for this one, we draw those in, fill this up. And how many total valence electrons have I used there? 32. So this is my drawing for this, my Lewis structure. Now, how many bonded atoms do I have here? 4. How many lone pairs? 0. So looking at your chart, 4 bonded atoms, no lone pairs. What shape is this? Tetrahedral. Now this is where the drawings start to come into play a little bit more. This is not drawn like this. This should be drawn something like that. And I know the book does something like these weird things. You don't have to do this. So you have something going back in the plane, something coming out of the plane, something sticking straight down. So this is carbon tetrachloride. This is where that 3-dimension viewing starts to really be affected if you can't visualize this. Models will help. We'll do models in the lab today, and you'll be able to see the actual structure of this. So this is carbon tetrachloride. That's the molecular shape. What about the electron geometry? It's the same, right? It's still called tetrahedral. How about the bond angle on this one?
109.5.
109.5. So the bond angle is talking about the angle between these adjoining atoms. So that's the bond angle. That's where they get that from. We forgot to mention that on the trigonal planar. That one was 120. Okay, questions on this one?
If there was a double bond, would the number of bonded atoms?
No. That's why they talk about the number of bonded atoms, not the number of bonds,
Okay.
because it's still just the one bonded atom. Okay, let's look at the last one there. Okay, so sulfur has how many valence electrons? How many valence electrons does sulfur have? 6. How many does iodine have? 7, but there's 6 of them. So we have a total of 48 valence electrons there. So for this, our skeletal structure, we just start off like anything else. We're going to just draw our lines, just acknowledging that this is going to have 12 electrons. Everything else still has 8 electrons. It's normal. Just that sulfur. So I'm going to fill in the rest of these. And when I do that, how many electrons have I used?
48.
There's a total of 48 electrons there. So for this one, that's on the second page of this, I have how many bonded atoms? 6. How many lone pairs? 0. So what would that be called? The molecular shape of it, sorry. Molecular shape. Molecular shape is octahedral. Yes, sorry. I'm for some reason staring at square planar right now. Wrong thing. Okay, so octahedral, what about the electron geometry? Same thing, right? So for this one, when you draw it, it's kind of, when you draw these things, it's kind of like there's 2 things sticking out at the top, and this is almost like a ring coming through the middle of it. So like there's like a straight line with the sulfur, the iodine, and then around the middle there's a ring that has more iodines on the outside of it. So that's kind of a picture of that. So that's the octahedral one. Any questions on that one? And what are the bond angles on that one? 90 degrees. Okay. Questions so far? So far we've done just kind of our easy ones. Are we seeing how to use this chart?
Yeah.
Okay. So let's look at some that start to give us a little bit of different shapes here. We have BH2 minus. So BH2 minus, what's going to go in the center? The B. And then what's going to be on the side? H and H, right? Okay, so boron has how many valence electrons?
3.
3. How many does hydrogen have? 1, and there's 2 of them. And then our negative charge tells us we're doing what? Adding 1, so we have a total of 6 electrons there, right? So I connect this, I have my 2 there, but boron likes to have how many valence electrons? 6. So I'm going to add in my 2 right there. That is my total of 6 electrons for boron. Hydrogens each have 2. Now for this one, how many bonded atoms do I have?
2.
2. How many lone pairs do I have?
2.
1.
A pair. It's a lone pair. So that's the 2 together. So this is a single lone pair. So I have 1 lone pair, 2 bonded atoms. So if I look at my chart, what is 2 bonded atoms and 1 lone pair?
Yeah.
The molecular shape, yeah. So if you look at this, you have your 2 bonded atoms, 1 lone pair. The molecular shape is bent. Electron geometry is trigonal planar. Now here's where the differences start to happen. So before electron shape and molecular shape, electron geometry have been the same. Now they start to differ. So here, that is kind of the shape of this. You don't have to really draw that cloud. I'm just kind of trying to show you the way it looks there. You have a bent molecule. This electron pair takes up space up here, and it actually takes up more space than these bonded atoms do. It has this electron repulsion up there. Remember, you have 2 negative electrons in very close proximity. The electrons, the negative charge, is not being shared amongst 2 different atoms, so it's going to push things away a little bit and bend them away from each other. That's why we get this bent geometry. So when you draw this, it should be drawn reflecting that bend right there. So you could draw it like that. That would be fine. So electron geometry is still that same trigonal planar shape, but the actual molecule itself, if you can't visualize those electrons, right? You can't see them, but you would be able to see the hydrogens and the boron. So you would see that looking through a very powerful microscope. But remembering that those electrons are there, that's why it actually looks like that. So we have our trigonal planar for the electron shape, but the molecular shape is going to be the bent. What is the angle for this one? 120, yeah. Okay, any questions on this? Okay, the next one. Oh, I forgot to do that, didn't I? Did I say the most common mistakes made? Yeah, you would put that in brackets with the charge. Yeah, so brackets, charge. Okay, any other questions on that one? The next one, Ni3. What's going to be the center atom here? Nitrogen. Okay, so for this one, nitrogen has how many valence electrons? 5. How many does iodine have? 7, but there's 3 of them, so we have a total of 26 right there. Okay, so I have nitrogen surrounded by my iodine. Draw my lines there. Nitrogen desires to have how many more electrons? 2. How about iodines? They each need 6 more, right? Okay, so when I do that, how many electrons have I used? 26. So that's my Lewis structure there. How many bonded atoms do I have here? 3. How many lone pairs?
1.
Am I hearing music?
Yes.
What is that? Someone's phone going off and they don't know about it? Sorry, I'm just like hearing this background noise continually. Okay, where was I?
Aren't you supposed to add, isn't there supposed to be a charge on that, so you would add or something? Or
No, there's no charge on this one.
Oh, okay.
Yeah, this is the only one in that series that doesn't have charge. Okay, so I have 3 bonded atoms. How many lone pairs do I have? 1. So according to my thing over here, I look for 3 bonded, 1 lone. What do I have? Trigonal pyramid. So it should look something like this right here when I draw it. So when I draw this correctly, it'll look something like that. And then you have your lone pair up there on the top. So this is trigonal pyramid. And then what is the electron geometry? Tetrahedral. It's the same. Anytime you have 4 sets of either electrons or bonded atoms, it's always going to be tetrahedral. So you'll notice that whenever you have 4, they call them domains, it's always going to have the same electron geometry right here. It's only the molecular shape that changes. So you can kind of see that trend right there.
Wait, what is the domain?
So this is a domain, that's a domain, that's a domain, that's a domain. So it's any electron pair or also an atom. So bonded atoms, lone pairs, the total of those add up to the total number of domains.
Okay, I see.
Okay, other questions on this one? Yes.
So we only put brackets on it if it's a negative charge.
Or positive charge for this, yeah.
So this one you put a bracket with a positive.
Yeah, which I think is the next one, yeah.
What's the best way to memorize these? Would you say it's the picture and the name, like the molecular shape and the electron geometry? Or would it be the bonded
I would go
atoms?
off of the bonded pairs, lone pair, or the bonded atoms, lone pairs. I would have a list that has those on the front and on the back. I would have the information that I need to know about that. Because that's what you're basing everything off of, is the bonded and lone pairs. So I would say something with 3 bonded pair or bonded atoms, no lone pairs is this. Something with 5 bonded atoms, 1 lone pair is this. That's what I would go off of.
And then when we get the molecular, are we drawing, you know how you change your drawing a little bit at the end?
When
Is
I
that
ask
the
for
molecular
you to
shape?
do, yeah, that's the molecular shape. And when I ask for you to do VSEPR on something, that means you need to draw it how it would look. So like I said, don't worry about drawing the shaded and dots and all that stuff, but just draw it in the relative shape of what it would look like. Other questions on that?
So we don't have to worry about the dotted lines and shaded?
No, you don't have to worry about that.
Okay.
Okay, ClF4+. Okay, for this one, what's going to go in the center? Fluorine. What's going around it? The fluorines, right? All right, how many valence electrons does chlorine have?
7.
And how many does fluorine have? 7, right? So we have 7 times 5 is 35. I have a +1 charge there. What does that mean I'm doing? I subtract 1 for a total of 34. Okay, so fluorine is one of our exceptions here. But let's just draw this in. Make all the fluorines content. That is 32 electrons right there. I need to use 2 more electrons, right? So this is a really good way of knowing that I have an exception in that center because I have 2 electrons left over. So I would put 2 electrons there in the center. So I have my 34 electrons that are now used. So according to this, how many bonded atoms do I have?
4.
I have 4. How many lone pairs?
1.
I have 1. So for this one, there's an eraser hidden right in the middle back there. What is this called?
A seesaw.
Okay, so we have a seesaw. Now, when you are dealing with the atoms that are in the 5 and 6 domains, there is a specific order for how you start to drop out atoms and replace those with electrons. And you need to get these right. So if you look at the seesaw, where does that electron pair go when you draw it? Does it go on the up and down or the side to side? So like the X or the Y? X or the Y? It goes on the X-axis, right, if you're thinking of a graph. So it goes into one of these. So you would replace one of these first. So when you are doing the 5 domains, you always replace that X-axis first. That's always going to be the one that's replaced. So we have 4 bonded, 1 not. Was this chlorines and fluorines? Yeah. So we would have something that looks like that. If you were to replace one of these with that electron pair, it is wrong. And that is because of the way the electrons repel themselves. If you look at the bond angles here, what is the bond angle of this molecule? 90 and 120. These are all 90 degrees apart. These are 120. So this is 120 right there, from this atom to this atom. The electron pair is going to come from the one that's the most crowded. It's going to minimize repulsion that way. So it's going to go over here, and then that way these ones over here are farther apart from it. So you have a bigger distance over there. So the electron pair goes into the X-axis. Electron geometry, still trigonal bipyramid, nothing different there. Questions on this one?
And you would put the brackets right? With
Yeah,
the
this one
plus
needs
on the
brackets.
outside?
And whoops, the positive charge. Okay.
Are you going to want us to draw the angles? Like,
You do not have to draw them exactly with angles now. You don't rip out the protractor or compass or whatever they are. I don't even remember what they're called. I don't care about that. Just estimate. Okay, last one. SF5 minus. So for this one, obviously the S is in the center, surrounded by our 5 Fs. How many valence electrons does sulfur have? 6. Fluorine has how many? 7 times 5, and then that -1 tells us to do what? Add 1. So we have a total of 42 electrons there. So for this one, if I fill these up, how many electrons have I used? 40. So I need to have another pair thrown in there to have my 42. So I throw that pair in there. So how many bonded atoms do I have here? I have 5 bonded atoms. How many lone pairs? 1. So if I look at what this is going to be drawn as, what's it going to be called? Square pyramid, right? Okay. So for these, now notice, 6 domains, you replace on the different axis as the 5 domains. Here we do our vertical axis. So on the 6 domains, you replace the up and down ones first. So for here, sulfur and fluorine. You draw it up there first. And then once again, you would have your charge. Yes.
Like in the picture, it says it has the cloud.
Oh, that
Underneath,
doesn't matter if you do it up or down, because that, I mean, I could flip this and it would be the same thing. Yeah.
Just not sideways.
Just not one of the sideways ones. Yeah.
better.
Yeah, practice will help a lot with these as we're doing this. A lot of practice on this. Okay, continuing on. I mentioned that this is important because we talk about something called electronegativity and polarity. And when we're talking about these, we need to understand the molecule shapes in order to be able to determine if something is electronegative, if it's polar, what we're looking at. So, electronegativity. What does electronegativity mean? The ability of an atom to attract electrons, right? Supposedly it's supposed to be showing my dot camera right now. And it's decided not to. Okay, so when we're talking about electronegativity, we're going to start off with something that's the simplest atom to understand, or compound to understand the difference between them. If you have something like hydrogen and chlorine, hydrogen has how many valence electrons? 1. How many does chlorine have? 7, right? So chlorine's over here with 7. They both want to have a full octet, or in this case duet. They want to have those full outer shells. So hydrogen does this by giving up its 1 electron. Chlorine accepts that 1 electron to get that full octet. Since this one has 7 electrons, how strongly do you think it's going to pull on this 1 electron here that they're sharing? Very strongly, right? So we have this shared bond right here. Chlorine is going to be pulling very strongly on that 1 electron because it really wants that electron to have that full octet. Hydrogen, how tightly do you think it's going to hang on to it?
Not at all.
It's going to pretty much, it's almost like an ionic compound here. Not quite as strong, but it's almost that difference. So what happens is we say that chlorine pulls on that electron a lot more. It has a lot more of a pull. It is more electronegative. So it's more at the negative charge of the electronegative charge. We draw this as a partial negative or a partial positive. So we say hydrogen has a partial positive charge, chlorine has a partial negative charge. This is what is known as a polar bond. You draw them with the arrow pointing towards the most electronegative element, in this case which is chlorine. When we talk about electronegativity, the most electronegative elements are on the top right-hand corner of the periodic table. Ignore hydrogen over there. So hydrogen belongs on the other side at this point. Fluorine is the most electronegative thing that forms the compound. So fluorine is very electronegative. Least electronegative, bottom left corner. So it kind of goes up at an angle. Okay, a dipole moment. What's a dipole moment?
The result of uneven electron sharing.
So it's, yes, and as a result of this uneven electron sharing, you have these partial charges that are actually developed that I just talked about. Whenever we have partial charges, that allows for an attraction. If you have something that's positive and negative that's nearby, you're going to have attractions there. So that's what this dipole moment is talking about. Polar covalent bonds. Bonds that are sharing the electrons unevenly. This is a polar covalent bond. You have hydrogen pulling on it more strongly than, chlorine pulling on it more strongly than the hydrogen. If I have this right here, 2 chlorines, do you think this is going to be a polar bond?
No.
No, why not?
Because they're pulling on it evenly.
They're pulling on it equally. There's 2 chlorines. They're both pulling. It's like a tug-of-war contest. They're pulling with the same strength. This is what we call a nonpolar bond. So anytime you have a completely symmetrical compound, it's going to be nonpolar. So symmetry is something to look for when we're talking about polar versus nonpolar compounds. If it's symmetrical, it is nonpolar. Okay. Let's see here. Okay, so we have different bond types on page 342 that you should have looked up. What were the different bond types? So we have our nonpolar, which is the pure. Then you have your polar covalent, and what else? Ionic. Okay. And then the electronegativity differences. For a nonpolar, what should your electronegativity differences be?
0.
What about polar?
Intermediate.
So, intermediate. Did anyone get actually numerical values for those?
0.4 to 2.0.
Okay, and then ionic is what?
2.0 plus.
So greater than 2.0. Now, you do not need to memorize individual electronegativity values. I will give you those if need be. However, what you need to be able to recognize is by looking at the periodic table, you should recognize, do I have ionic compounds? How do we know we have something that's ionic?
Metal and
nonmetal, right? You don't need to know values. You can just say, oh, metal, nonmetal, it's ionic. How do I know if I have something that's polar?
They're unequal.
They're unequal, they're not symmetrical, and we just talked about the trend. If I say that I have arsenic with fluorine, arsenic is down bottom left, whereas fluorine's the top right there, there's going to be a difference in strength. So you know that that's going to be a polar bond. So those types of trends you need to be aware of. Okay, so that's I just drew the examples there for that one. Okay, so polar bonds, we're only looking at the strength of two atoms. It is different than a polar molecule. Polar molecules, you're looking at the overall picture. So let's look at something like CCl4. If I look at the structure of CCl4, that's the Lewis structure of CCl4, but this will work for now. The difference between carbon and chlorine, is that going to be a polar bond right there? Look at carbon, look at chlorine.
Yes.
What do y'all think?
Yes.
It is. Chlorine's going to be much more polar than carbon. It's going to be pulling on it a lot harder. So each of these bonds is actually going to be pulling like this. Now, you know anything about vector addition? If you look at that, what's going to happen to the overall pull on that molecule? Is any one side going to pull more strongly than another side?
No.
No. The overall difference of all of those things pulling is they're all pulling with the same amount. This is a nonpolar molecule. So even though you have polar bonds right here, you have a nonpolar molecule overall. The strength of those vectors cancels out. So if I were to draw this in the actual VSEPR, imagine that in 3 dimensions, those would all cancel out. So that would end up in a nonpolar molecule. Now, one of the ways you can look to determine if something is polar or nonpolar is actually the next question here. A clue. What are some of the clues to determine if you have a polar molecule? What are you looking for?
Do you have like
Your
polar
degrees?
bonds?
The what? A difference in electronegativities? If I just want to look at a molecule and determine if it's polar or nonpolar, what's something I can look at to just right away say, oh, that has to be polar?
If it has a 3-bond polar bond and it's 109.5 degrees, it will not cancel.
Okay, so if it's 109.5, okay. Also, symmetry. That was the big one I was looking for. If it is not symmetrical, it is polar. So if there's no symmetry, that means it's polar. There's one other thing that just screams, I have a polar molecule. And it holds with polyatomic ions especially.
Charges?
Charges. So if you have a charge, oops, not nonpolar, you have a polar molecule. So those are two things that scream that it's a polar molecule. And then the 109, so like the trigonal planars, all those are going to be a lot of times. And also, oh, there's one other thing too. And this has to do with VSEPR. Lone pairs, yes. Any lone pairs. It's going to be polar. So there's a few things you can look at, and that kind of screams to you that these are polar molecules. If you have a lone pair, it is polar, because the lone pairs pull more strongly than a bonded atom will. I have a timer out. Yeah. Okay, so we'll finish that up in lab. That won't take too long to finish the rest of these. Any questions before y'all leave? Okay, that's it then. You have a quiz on Thursday, right? So it's on chapter 9. I haven't written it yet, but it'll be on chapter 9.